NumPy is an extremely powerful tool and one of the most important ones if you want to get into data science or any field where Python is used and you have to deal with numeric computations. Learning NumPy alone is enough to get you far ahead of those who do not use it. In this single video, you will learn the most useful parts of NumPy, and by the end of it, you'll be pretty much comfortable using it when solving problems. So treat it like a Kickstarter for your NumPy journey. The plan is simple. We will look at what is NumPy and why we should use it. And next we look at the data structure NumPy is using and the functions that let us manipulate this data structure. So NumPy stands for numeric Python. This is a Python library widely used in engineering and science, specifically when dealing with numbers, vectors, matrices, or tensors. It lets us do faster computations and has many extremely useful pre-written functions. Also, it is widely used by the community, so most other tools like machine learning or data analysis packages use NumPy or have methods to be used together with NumPy. In this short course, I will use Jupyter Notebook to write my code. Specifically, I will use Google Colab as this won't require any additional setup. I'll leave the download link for this notebook with all the code in the description below, so if you don't want to type the code yourself, you can still follow along. So let's open a fresh notebook and start learning. Okay, so the core data structure in NumPy is the ND array. It is a multidimensional array of fixed size items, and an ND array object represents a grid of values of the same type, so it can be one-dimensional, two-dimensional, or higher dimensional grid of elements. There are multiple ways to create these arrays, so let's explore the ones used most often. At first, we import NumPy as NP and we execute this cell with Shift and Enter keys. We can create an array from the existing Python list by simply calling np.array and passing our list. And we can print the result and its type to confirm that everything works as expected. We can see that this indeed is a NumPy array. And we can do the same by passing a tuple. Our list doesn't have to be one-dimensional. If we pass a list of lists, it will create a two-dimensional ND array. Here we go. Sometimes we don't have existing variables and we want to generate arrays filled with some values. So NumPy also has methods for that. For example, np.arrange lets us create an array with evenly spaced values within a given range. So if we type np.arrange and pass 1, 10, and 2, we get an array with elements from 1 to 10 with a step of 2. And if we type np.linspace and pass 0, 1, and 5, it generates an array with a specified number of evenly spaced values between start and end values. So 5 evenly spaced values between 0 and 1. There are also a few ways to generate random arrays. So np.random.rand will create an array with random values from a uniform distribution. And in this case, this array will have 3 rows and 2 columns. And if you write np.random.randn, this will create a similar array, but this time values are sampled from the standard normal distribution rather than uniform. np.zeros creates an array filled with zeros, and np.ones creates an array filled with ones. If we want to create an identity matrix, we can use np.I or np.identity. This function will create an array in which the diagonal is filled with ones and all other values are zeros. For all arrays, we can check the number of dimensions it has with ndim. So if the array is 2-dimensional, it returns 2. If it's 3-dimensional, it will say 3. We can access its shape by writing .shape, and it will give us a tuple representing the dimensions of our array. So for example, the number of rows and columns for a 2D array. .size will give us the total number of elements in the array, and all arrays also have a data type that can be accessed by .dtype. Next, we want to select elements from our array, so you can access a specific element in a NumPy array using its index. So here, if we pass 2, it selects the third element as the index starts from 0. For multi-dimensional arrays, we use multiple indices. So if we pass 1 and 2, it selects the element in the second row and third column. Slicing lets select a subarray. So if we pass 1, 4, this selects elements from index 1 to 3, as index 4 is not included. Boolean indexing is also possible. So if we pass a condition, it selects elements, in this case, greater than 5, because that's the condition. Sometimes it is useful to reshape our arrays, so there are a few ways to do that. If we have a matrix and want to find the transpose of a matrix, we can simply write .t and get an array where rows became columns and columns became rows. Or we can reshape our array using .reshape and pass a new shape. But to use it, the product of the dimensions in the original shape must be equal to the product of the dimensions in the new shape. So here we reshape the matrix that is 2 by 3 elements to an array that is 1 by 6. So far so good, but now let's see what we can do with these arrays. So there are element-wise operations. We can add, subtract, multiply, or divide. And we can do that with arrays of the same shape. And each operation will result in a new array. We can also compare two arrays and get an array of booleans. There is a way to perform element-wise operations with arrays that are not of the same shape. This is a NumPy's feature called broadcasting, and it enables element-wise operations without manually reshaping or replicating arrays to match each other's shape. So broadcasting automatically stretches the smaller array along its dimensions to have the same shape as the larger array. So if you have 3 by 4 array and want to add an array with only one row and 4 elements, it will automatically replicate that row until it matches the shape of the first array, making the operation possible. And there are more intuitive element-wise operations like multiplying an array by a number or raising it to a power. This operation will be performed on every value of the array. Aggregation functions let us compute some statistics like np.sum, which will add all the values and return a sum. We can also sum along the specific axis. So if we have a matrix and want to find the sums of row values, we can use np.sum and pass axis equals 1, and we get 3 sums as our array has 3 rows. np.sum with axis equals 0 will add our rows. We find the smallest value with np.min, the biggest value with np.max, and the mean with np.mean. For standard deviation, we use np.std. If we want to combine two arrays, there are functions like hstack that stand for a horizontal stack. So it stacks the arrays side by side. Joins along the horizontal axis. Here's the example. And if we want to stack on top of each other, we can use vstack, which stands for vertical stack, and here's an example of that. If you want more flexibility, you can use concatenate, which lets you specify the axis along which to combine those arrays. So axis equals 0 will combine vertically or along rows, and axis equals 1 will combine horizontally or along columns. The arrays must have the same shape along the axis that is not being concatenated. For example, if you concatenate along rows or axis 0, the arrays must have the same number of columns. Okay, so now it's time for what are, in my opinion, the most important or the most powerful NumPy functions, and these are linear algebra operations. So the first one is matrix multiplication, and in NumPy you can perform matrix multiplication using np dot or the add operator, and this returns a new matrix, which is our multiplication result. The same dot operation can be used to find the dot product of two vectors. To find the magnitude of the vector, we can use np.linalg.norm, and the same operation can be used to find the Euclidean distance between two vectors. This is useful when we want to compute the cosine similarity of two vectors. So first we normalize them, or in other words, perform element-wise division by vector length and calculate the dot product. And this number is the cosine value of the angle between those vectors. We already discussed the transpose operation, so it's simply adding dot t to our variable. The last part is saving and loading arrays, which is useful when you want to reuse your data later. So you can use np.save and save your NumPy array to a file. And this function saves array to a file with the extension .npy. It takes the path and the array itself. To load the array from the file, we can use np.load function, which simply takes a path to our previously saved array and reconstructs it from that file. And this is it. Of course, NumPy has a lot more features, a lot more functions that we can discuss in this short course, but I believe these are the main things that will get you going. So if you find this video useful, hit the like button and consider subscribing, and I'll see you in the next one.